Imagine knowing your home, like really intimately. You walk its halls, see its rooms every day, always from the same perspective, standing on the floor,
Yeah.
looking
Yeah,
around.
your standard view.
Exactly. Now, what if you could suddenly see your home from directly above, maybe hovering over the roof, or even floating up from the basement looking at the underside of the floors? It'd change everything you thought you knew.
That's a perfect analogy, actually, for what's happening right now with our sun. We've been watching it for, well, forever, but almost always from just one angle, a flat viewpoint.
Right. And that's what we're diving into today, these incredible new ways of seeing our nearest star, perspectives we're getting from a really groundbreaking thing called Solar Orbiter.
Yeah, our goal here, you could say, is to unpack what makes Solar Orbiter's view so unique and explore some of the first really fascinating discoveries it's already starting to beam back.
And why these observations aren't just cool science facts, right? Why they're actually set to totally transform how we understand our star.
Exactly. We're going to look at how this spacecraft is literally tilting its view, looking down or maybe up on parts of the sun we've never, ever been able to properly image before.
And what its instruments, these really cutting-edge instruments, are showing us for the first time.
And how that could impact, well, everything from predicting space weather, the stuff that affects our technology here on Earth, to unlocking the sun's fundamental secrets, how it works, how it behaves.
Okay, so let's start with that perspective shift. Because like you said, for ages, even with space telescopes, our view's been pretty limited.
It really has. I mean, think about it. Earth orbits the sun. All the other planets are basically in the same flat disk, more or less.
The ecliptic plane,
That's
right?
the one. And most spacecraft we've sent up close to the sun, they've also stayed in or very near that plane. It's actually tilted just a tiny bit relative to the sun's own equator, maybe 7 degrees or so.
So we've always had this great view of the sun's middle, its equator. That's where we see the big sunspots, the dramatic stuff.
Yeah, the active regions. But the top and bottom, the poles, they've essentially always been hidden or at least seen at a really awkward grazing angle. It's like trying to understand a whole globe by just staring at the equator line.
Hidden from view. But we know they're super important for how the sun behaves, don't we?
Oh, fundamentally important. And this is where Solar Orbiter just changes the game completely. It's designed specifically to leave that flat plane, to actively tilt its orbit out of it to get those high latitude views we've been missing.
And it's actually started doing this. This tilt isn't just on paper anymore.
It has. It's incredibly exciting. Just back in February 2025, Solar Orbiter officially kicked off its high latitude journey.
How did it do that? Just fire its rockets.
Well, it used a really clever trick, a precisely timed flyby of Venus. It used Venus's gravity like a slingshot.
Ah, gravity assists.
Exactly, to bend its path and tilt its orbit. Right now, it's at an angle of 17 degrees relative to the sun's equator.
17 degrees. Okay, like you said, maybe doesn't sound like a huge amount, but for the sun, that's like climbing a ladder to look at your house instead of standing on the ground. You see different things.
Monumental difference. You start seeing parts of it you literally couldn't see before. And it's worth maybe comparing this to the only other mission that went out of plane. That was Ulysses, a joint ESA-NASA mission back in the 90s.
Right, I remember Ulysses. It went over the poles too, didn't it?
It did, which was groundbreaking. It measured the solar wind and magnetic fields directly up there for the first time. Huge step.
But it didn't look at the sun, did it? It was more sampling the environment.
You got it. Ulysses didn't have any cameras, no imaging instruments. Solar Orbiter is the first mission ever that has telescopes to actually image the sun's poles. And it's doing it while flying much closer than Ulysses did.
And it's sticking around, watching how things change.
Critically, yes.
Yeah.
It's designed to watch the poles evolve over the sun's whole 11-year activity cycle.
So it's not just a snapshot. It's a long-term movie from a new angle.
Yeah.
You mentioned seeing parts never imaged before. Is there a specific example from this 17-degree view?
There is. The team released this comparison view from March 23rd, 2025. Solar Orbiter was 17 degrees below the sun's equator. And boom, you can see the South Pole directly in the image from Earth. Impossible. It finally gives us visual context for those measurements Ulysses made decades ago.
Seeing the bottom of the sun. That's wild. And 17 degrees is just the start, I hear. It's going higher.
It is. Daniel Miller, he's the ESA project scientist for Solar Orbiter. He called this first tilt just the first step of Solar Orbiter's stairway to heaven.
Stairway to heaven, love that. So where does the staircase lead?
Higher up. It'll orbit around 17 degrees for a bit, but then another Venus flyby, this one's set for December 2026. That'll bump the angle up to 24 degrees.
Okay, getting steeper.
And the ultimate goal, the highest it's planned to go operationally, is by June 2029. It'll reach a remarkable 33 degrees inclination.
A third of the way to looking straight down.
Pretty much. As the teams keep saying, the best views are yet to come. It's still climbing.
Incredible engineering. Okay, so we get the unique angle. Now, the tools. What's it actually using to see from up there? You said it's packed with instruments.
It really is. People often call it the most complex science lab ever sent to study the sun. It's carrying 10 state-of-the-art scientific instruments, all of them collecting data right now.
10? Wow. But these first images, the ones causing all the buzz, they come from 3 main ones.
That's right. These initial really game-changing images are primarily from 3 imagers. There's the polarimetric and helioseismic imager, that's PHI.
Okay, PHI.
Then the extreme ultraviolet imager, or EUI.
EUI. Got it.
And the spectral imaging of the coronal environment, which is SPICE.
PHI, EUI, SPICE-T. Okay, let's unpack those. What does each one do? What piece of the puzzle does it give us?
All right, starting with PHI. This one looks at the sun in visible light, kind of like our eyes see it, but its real trick is mapping the sun's surface magnetic field.
Ah, the invisible magnetic fields.
Exactly. It shows where the field lines are pointing in or out areas of north and south magnetic polarity. It's led by a team in Germany at the Max Planck Institute.
So it sees the sun's face, but also maps out its magnetic skeleton.
That's a good way to put it. Crucial for understanding what drives solar activity. Then you have EUI. That's led by folks in Belgium. EUI images the sun in extreme ultraviolet light.
Invisible to us.
Right. And this light reveals the super, super hot gas, millions of degrees, that makes up the sun's outer atmosphere, the corona.
The halo you see in an eclipse.
Precisely. EUI shows us that dynamic, swirling plasma of the corona where a lot of the explosive action happens.
Okay, so hot outer atmosphere. And the third one's spicy.
SPICE. This one's led from France. It's an imaging spectrograph, so it doesn't just take a picture. It analyzes the light coming from specific chemical elements in the sun's atmosphere.
Like what elements?
Things like hydrogen, carbon, oxygen, neon, magnesium. Each element in a certain state gives off or absorbs light at very specific wavelengths, like a barcode.
A chemical barcode for the sun's layers.
Exactly. By tuning into these wavelengths, SPICE can map where these elements are and what conditions they're in, often at known temperatures. So it lets us see different layers, like the chromosphere just above the surface, or the transition region.
The transition region, that's where the temperature goes crazy high.
Yeah, it skyrockets from maybe 10,000 degrees Celsius at the surface to hundreds of thousands, even millions. As you go out into the corona, SPICE helps map that layer.
So PHI, surface magnetism, EUI, scorching hot corona, SPICE, dissecting the layers by chemicals and temperature.
That's the core idea. And the real magic happens when you use all 10 instruments together. Comparing data from PHI, EUI, SPICE, and the others lets scientists build this complete 3D picture. How stuff moves, how energy flows, how the magnetic field drives it all. Especially now in those polar regions we couldn't see properly before.
You mentioned new phenomena, like polar vortices, like in Jupiter or Saturn.
It opens up the possibility. We don't know if the sun has them, but now we can actually look. Do giant swirls exist at the sun's poles? It's the kind of thing Solar Orbiter might discover.
A solar vortex. That's a pretty wild thought. Okay, so we've got the tilt, we've got the amazing instruments. What are the first big discoveries? What are they actually seeing up there at the poles?
Yeah, this is the really exciting part. As Professor Carol Mundell, she's ESA's Director of Science, said, these are genuinely humankind's first ever views of the sun's pole. And Professor Sami Solanki, the lead for PHI, he basically said the poles were terra incognita for solar scientists, unknown land.
And the first reports, the magnetism isn't quite what was expected, a bit messy.
That's the word they're using. One of the very first major findings from these polar views from the PHI instrument is that the magnetic field at the sun's south pole right now is, well,
a mess.
a mess. Oh, so I thought poles were simple, like north here, south there.
You'd think it would be like a simple bar magnet, wouldn't you? A clear north pole, a clear south pole. But PHI is showing us something totally different at the south pole currently, instead of one dominant polarity.
It's all mixed up. Exactly. It's a complex jumble. Patches of north polarity right next to patches of south polarity, all mixed together across the whole polar region.
Like a magnetic patchwork quilt. Or like iron filings scattered randomly.
That's a great visual. Speckled, complex on small scales, not one big uniform region. But here's the crucial thing. This messiness isn't random. It's actually perfectly timed with where the sun is in its cycle.
Ah, okay. We're heading toward solar maximum now, peak activity.
We are, or very close to it.
Yeah.
And this messy state at the poles, it happens specifically around solar maximum. This is the exact time when the sun's entire global magnetic field is doing its big flip.
The 11-year flip, where north becomes south and south becomes north.
That's the one. The magnetic poles are literally swapping places. So this mess we're seeing at the pole is a direct visual sign of that huge magnetic rearrangement happening across the entire sun.
Wow. So Solar Orbiter caught it right in the act of flipping.
Pretty much. It's a snapshot of the sun's magnetism in turmoil as the whole field structure reconfigures itself. It's temporary, this messy phase. Once the flip is complete, a single dominant polarity should gradually take over at each pole again.
And it'll become more ordered, more like that bar magnet idea as we head towards the next solar minimum in 5 or 6 years.
That's the expectation, yes. Which means Solar Orbiter didn't just get to high latitudes, it got there at the perfect time.
Unbelievable timing.
Sammy Solanke said it perfectly. Solar Orbiter reached high latitudes at just the right time to follow the whole process from its unique and advantageous perspective. We're getting a ringside seat to the sun's magnetic field flip, seen from the poles.
Does the view of the whole sun from PHI add context here? Like, where is the strongest magnetism overall?
It does. When you look at the full disk image from PHI, you still see the really strong magnetic fields are concentrated in bands nearer the equator. That's where sunspots and active regions form the source of most big flares and eruptions.
So the poles are messy now, but maybe not as magnetically strong as the equatorial regions?
In terms of field strength in large structures, yes. The poles have these weaker, complex, small-scale fields, especially during this flip. The powerhouse stuff is still concentrated lower down. But understanding the poles is key to the whole global picture.
Why is understanding the polar part so critical?
Because it's fundamental to the sun's global magnetic field, the dynamo that generates it, and the whole 11-year cycle. Why does the field flip? How does it regenerate? The poles are where the large-scale field lines emerge and re-enter, so understanding their behavior, especially during the flip, is crucial for figuring out the entire cycle.
And that feeds back into predicting solar activity and space weather.
Absolutely. Get a better handle on the cycle, you get a better handle on predicting its consequences.
Okay, so messy magnetism linked to the flip, it's huge. What about the solar wind? That constant stream of particles blowing off the sun. That was another big goal for Solar Orbiter, right? Understanding where it comes from.
One of the primary science questions, yes. And here again, the SpaceInfo instrument has delivered something groundbreaking. Using those spectral measurements we discussed.
The chemical barcodes.
Exactly. The SpaceInfo team has, for the first time, used Doppler measurements to actually track the speed of solar material moving in different layers of the sun's atmosphere, viewed from this eye latitude.
Doppler. Like the ambulance siren sound-changing pitch. Higher towards you, lower away.
That's the principle. Light waves do the same thing. If the stuff emitting the light is moving towards Solar Orbiter, the wavelength gets squished a tiny bit blue shifted. If it's moving away, it gets stretched red shifted.
So SpaceInfo measures those tiny shifts in the barcodes for elements like carbon.
Precisely. And from that shift, they can calculate how fast that material is moving, either towards or away from the spacecraft.
So they can actually see plasma flowing outwards
Mm-hmm.
and measure its speed.
They can create these velocity maps. For instance, using carbon ions in the transition region, they can map out areas moving towards or away. Darker colors might show faster flows, perhaps hinting at small plumes or jets shooting material outwards.
And connecting those flows, seen from this angle, to the solar wind, that's the breakthrough.
That's the key. These Doppler measurements, looking down on the source regions at the poles, are critical for figuring out exactly how and where particles get accelerated and launched to become the solar wind.
The wind that fills the solar system and hits Earth.
Right, and we suspect the poles are major sources, especially for the fast solar wind. Understanding that origin process is core Solar Orbiter science.
And we just couldn't measure this properly before from our usual flat view.
Not effectively. As Frederico Scher, the Spice Team lead, pointed out, previous missions were hampered by the grazing view. You were looking sideways at the base of these flows. Getting these direct Doppler speed measurements from above the pole, he called it a revolution in solar physics.
Seeing the launch pad from above, essentially.
Exactly, watching the solar wind being born.
Okay, so incredible stuff. First, direct views of the poles, seeing the magnetic mess during the flip, actually measuring the speed of outflows that become the solar wind. But let's bring it back home. Why does all this matter to us, living our lives here on Earth?
Right, the so what question. Well, the sun gives us light and heat, obviously essential, but it's also, as Prof. Mundell said, a potential disruptor.
Space weather, you mentioned it earlier. Flares, CMEs.
Coronal mass ejections, yeah. Huge eruptions of plasma and magnetic fields. When those hit Earth's magnetic shield, they can cause real problems.
Like knocking out satellites.
Yeah.
Affecting GPS, communications.
Definitely. They can disrupt radio signals, pose risks to astronauts, and in really extreme cases, they can induce powerful electrical currents in power grids on the ground.
Causing blackouts, potentially.
It's happened before, and it's a major concern. Our modern society is incredibly reliant on technology that's vulnerable to this solar activity.
So understanding the sun's magnetic field, the flip, how the solar wind is generated, it's all directly linked to protecting our infrastructure.
It is. Because what drives all that space weather? The sun's dynamic, changing magnetic field, understanding the cycle, the flip, how the wind is made, especially from the poles, which seem to funnel the fast wind that's fundamental to improving our forecasts. When will a big event happen? How strong will it be?
So these first views, these measurements, they're not just fascinating science, they're practical tools for improving space weather prediction, helping us prepare.
That's exactly the connection. And these are just the first views. Solar Orbiter is going to keep climbing, keep watching for years. It really is the start of, as they say, a new era of solar science.
Yeah.
We're getting the data we need to understand our star better and ultimately predict its behavior better.
It's pretty humbling, isn't it? How much we still have to learn about the star that makes everything possible here.
It really is. So, yeah, to kind of wrap it up, Solar Orbiter is giving us these first ever direct images of the sun's poles by tilting its orbit, starting its climb up that stairway to heaven.
And even from this first 17-degree step,
We're seeing surprisingly complex, messy magnetic fields at the poles, catching the sun right in the middle of its big magnetic flip. And instruments like SpaceInfo are making revolutionary measurements, actually tracking the speed of material being launched outwards to form the solar wind, especially from those polar regions we couldn't see well before.
it's all about peeling back the layers, figuring out the solar cycle, how that constant wind gets going.
Yeah, getting a much deeper, more complete understanding of the engine that drives the whole solar system.
Which definitely leaves us with something to think about. Given that the sun's complex, flipping magnetic field and these unpredictable bursts of solar wind can have such a big impact on our technology, satellites, communications, even power grids down here, as we get this much deeper understanding through missions like Solar Orbiter, how much more resilient do we really need to make our society, our infrastructure, to handle whatever our dynamic star might throw at us next?